Hello and welcome to another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 10, Lesson 7 on the vertex form of a quadratic function. This is a really neat topic and it's really the culmination of basically everything that we've done in Unit 10, which not surprisingly means it's the last lesson of Unit 10. And today what we're going to be doing is looking at various forms of quadratic functions, but then honing in and concentrating on a very useful form of a quadratic function known as the vertex form. Anyway, let's kind of get right into it. Now, various forms of quadratic functions. We have extensively studied quadratic functions. I mean, we really have. Especially back in Unit 8, we looked at them a lot. Those that have a degree of 2 and have a shape of a parabola. We can write these functions in a variety of forms that reveal different characteristics about the function. So let's take a look at exercise 1 and talk about a couple different forms of a quadratic function. For the quadratic function f of x equals x squared minus 6x plus 8, answer the following questions. Letter A, what is the quadratic's leading coefficient? All right, that should be a piece of cake. It's been a little while since we've talked about the leading coefficients of polynomials, but that should be real easy, and trust me when I say I've left you way more room than what you need here. Why don't you go ahead and write down the leading coefficient? All right, now remember, coefficients are always numbers, okay? Unless they're letters that stand for numbers. But anyway, in this case, it's the number that multiplies x squared, and that's equal to 1. Oftentimes we represent the leading coefficient of a quadratic with the letter a, so I'm going to say a is equal to 1. Even though that 1 isn't written, I'm going to have it down there. Now, letter B. Write the function in its factored form. So right now, let's be very clear. This function currently is written in what's called standard polynomial form, right? And the only thing that that's good for is to basically see the y-intercept, right? The y-intercept of this parabola is equal to 8. That's basically the only thing we can really get out of that form. But now let's write it in factored form. In other words, meaning that I'm going to write down f of x equals, and then I'm going to factor the right-hand side of that parabola, or I'm sorry, of that quadratic function. And this is a standard trinomial with a leading coefficient of 1. So I'm looking for two numbers whose product is positive 8 and whose sum is negative 6. That means both numbers have to be negative, right? And those two numbers happen to be negative 2 and negative 4, right? Because negative 2 times negative 4 is positive 8, and negative 2 plus negative 4 is negative 6. So I can write this as x minus 2 times x minus 4. And again, I want you to really understand something. This function and this function are the same function. It's just that this one's written in what's called standard form. This one's written in factored form. Now, factored forms of polynomials are important, and we saw them a little bit earlier this year when we were looking at cubic functions and quadratic functions back in Unit 8. All right. What's nice about the factored form of functions is that you can see one feature in them almost automatically. Let's take a look at letter C. What graphical features does the form in B help you identify? State their values. In other words, right, standard form, all I can see is the y-intercept. It's positive 8. But in factored form, there's something else you can see very simply. Pause the video now and see if you can figure out what that is. All right, well, what I can see in factored form very simply are the zeros of the function, right? So I can identify the zeros very easily, and those two zeros are x equals 2 and x equals 4, right? It's simple, right? If I put 2 into this function, I'd get 0 times negative 2, which is an output of 0. If I put 4 into this function, I'd get 2 times 0, which would be 0, right? So I can see the zeros. Now let's take a look at letter D. What is the axis of symmetry of this function? What is its turning point? All right, well now this is a little bit harder. We can't really see the axis of symmetry either in the original form or in the factored form. But see if you can figure out what the axis of symmetry is and what the turning point of this function is without using your calculator. Pause the video now. All right, well, there's two ways to find the axis of symmetry. One way is using the axis of symmetry formula. That's x equals negative b divided by twice a. Nothing wrong with that. But let's take advantage of symmetry right now. Remember, the axis of symmetry will simply be the average of the two zeros. So in other words, the axis of symmetry will be equal to 2 plus 4 divided by 2, which is 6 divided by 2, and that's 3. By the way, I shouldn't really even need to do that. I should know that the axis of symmetry lies halfway in between the two zeros, and if I have one 0 at 2 and one 0 at 4, then my axis of symmetry is at 3. Now, how do I find my turning point? Well, my turning point is simply, the coordinate point where it changes direction, and I know the x-coordinate of it already. I just need the y-coordinate, right? The axis of symmetry always passes through that, and you know what I think? I think I'm going to use the factored form of the function to figure it out, right? I'll have 3 minus 2 times 3 minus 4. That's going to be 1 times negative 1, which is negative 1. That's my y-coordinate. So my turning point is at 3 comma negative 1. And one thing is very, very clear to me, right? In the standard form and the factored form, the turning point is not obvious at all, right? The turning point, another name for it, is the vertex point of the parabola. That's not obvious at all when I look at the standard form. But now let's start to work towards that. Any quadratic function whose leading coefficient is equal to 1, like what we had in the last example, is just a horizontal or vertical shift of the simple parent function y equals x squared. Now let's play around with that idea a little bit. Exercise number 2. The function f of x equals x squared is shown graphed. The function g of x is defined by the formula g of x equals f of x minus 6 minus 4. Letter A, give a formula for g of x in terms of x. Do not write it in standard form. All right, well, let's do this together. Again, keep in mind, right, forget about the minus 4 for a second. If I just said g of x equals f of x minus 6, then I want to put an x minus 6 anywhere there's an x in this formula, right? Now, what will that give me? That will give me x minus 6 squared. So if g of x was just f of x minus 6, and f of x is x squared, then g of x would be x minus 6 squared, okay? But then I need to subtract a 4 overall. Now, what I wouldn't want to do right now, because it says do not write in standard form, is I don't want to square out that x minus 6 and collect like terms. If it said write it in standard polynomial form, I would want to, but it doesn't ask me to do that, so I'm not going to. Now let's take a look at letter B. How will the graph of g of x compare to that of y equals x squared? Well, this is what we did with horizontal and vertical shifting, right? I subtracted 6 from x directly, and that's going to move it 6 units to the right, right? Then I've subtracted 4 overall, and that's going to move it 4 units down. So g of x will be y equals x squared shifted 6 units right and 4 units down. Awesome, right? Now, letter C asks me to produce a graph of g of x on the same grid. Now, we're not going to create a table of values. What we're going to literally do is take all the nice points on here, and we're going to move them. We're going to take those things, and we're going to move them 6 units to the right, and we're going to move them 4 units down. So let's do it, right? I'm going to start with this point. I'm going to go 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. Take this one, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. The turning point, very important, right here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. I can just keep doing that. And I can then get this, and that's my function g of x. Okay? Simple. Now, by the way, notice, where is the turning point of this function? The turning point of this function, I know I didn't ask about that here, but the turning point of this function is at 6 comma negative 4. And do you already see how that 6 comma negative 4 is showing up in the formula itself if it's written in this particular form and not standard form? So let's now think about that a little bit and take a look at letter D. A third quadratic function has the formula h of x equals x plus 2 quantity squared plus 1. Where will this function have its vertex, its turning point? Explain how you determined your answer. Okay, well, pause the video now and see, without using your calculator, if you can figure out where this function will have its turning point based on shifting the simple parent function y equals x squared. All right, well, h of x, right, let's just write this down. H of x will be y equals x squared. I'm almost giving you the answer, like the explanation before giving the answer. H of x will be y equals x squared shifted 2 left and 1 up, right? 2 left and 1 up, right? I add 2 directly to x, it shifts it to the left 2. I add 1 overall, it shifts it up 1. So how can I figure out my turning point based on that? Well, the point is this thing has a turning point at 0, 0, right? So our new one will now have a turning point at negative 2 comma 1, right? I take my 0, 0, I shift it 2 units to the left and 1 unit up, and it now has a turning point at negative 2 comma 1. Let's take a look at letter E. Create a table of values for h of x and draw its graph on the grid above as well. All right, and what we'll do is we'll end up drawing it down here just because I don't want to have to keep going up there. So let's take a look at it. Let's get out of here. Open this thing up. I think I'm going to throw in x squared just so that we have it as kind of a, a benchmark. Then let me go in and enter another function in there. Now remember, this is going to be x, just to make sure I've got it, x plus 2 quantity squared plus 1. All right, enter. And notice, before we even figure out the table of values, right, it has definitely been shifted 2 units to the left and 1 unit up. Okay, but now I do want to follow the directions. I'm going to go into my menu. I'm going to grab my table of values. I need it not for F1, but for F2. Thank you, calculator, for asking me again about that. All right, I'm going to, just go up a little bit so that I can figure out some nice points here, right? So I'll have negative 4, 5, negative 3, 2, negative 2, 1, negative 1, 2, 0, 5, etc. All right, let me go to my handheld, full screen, come down here. We'll generate a table of values, maybe right here for h of x, x and y. So I'll do negative 4, 5, negative 3, 2, negative 2, 1, negative 1, 2, 0, 5. Maybe I'll go one more, 1, 10. All right, so negative 4, 5, negative 3, 2, negative 2, 1, negative 1, 2, 0, 5, and 1, 10. And then there'll also be a 10 over here. And that would be h of x. And let's put that thing back away. Okay, so there it is. And again, it's reinforced the fact that our turning point, right, is at negative 2, 1. Remember, we can always see that in a table by looking at that symmetry around that point in terms of the y values. Now, where is this all leading us to? Well, since the simple parabola y equals x squared has a turning point or a vertex at 0, 0, and that's really the key. If this thing didn't have a turning point at 0, 0, way bigger headaches, okay? But since it does, it's easy to see the coordinates of any parabola if it's written in its vertex form, all right? And let's see what I mean by that in exercise number 3. For each of the following parabolas written in vertex form, identify how the graph of y equals x squared would be shifted to produce the function, and then the coordinates of its turning point. So this thing is so great, right? Now again, it'd be a pain if these weren't written in this form, but when I look at A, which is y equals x minus 8 quantity squared plus 5, and I look at y equals x squared, I can say, oh, okay, the x minus 8 makes it go to the right 8 units, and the plus 5 makes it go up 5 units. So we've got right 8 up 5. Okay, so x minus 8 makes y equals x squared go to the right 8, and plus 5 then makes it go up 5. What's great now is I can now say that 0, 0 then ends up going to 8, 5. And that is the turning point of this particular parabola. If I slap that into my graphing calculator, I created a table of values, all of that, I would say it had a turning point at 8, 5. All right, pause the video now. Describe again the shifts that would have to occur to the parent function to produce each of these, and then use those shifts to determine where the turning points of both of these parabolas are. All right, well, the fact that I've got x plus 6 here, right here, means that I've gone to the left 6. The fact that I've got a plus 1 here means I've gone up 1. So I go left 6 up 1, which means now 0, 0 becomes negative 6, 1, and that is my new turning point. Okay, and in this particular one, right, that minus 7 tells me that I'm going to go to the right 7, right? This one's going to be shifted to the right 7, and then subtracting 10 overall means that I'm going to go down 10. So I go right 7 down 10, which means 0, 0 gets mapped to 7, negative 10. Excellent. It's so easy to see the vertex or the turning point when it's written this way, right? Now, in both geometry and algebra 2, you'll play around with how to use the method of completing the square to take a parabola that's in standard form and to write it as a parabola in vertex form. For now, we're not going to worry about that. We're only using completing the square to solve quadratic equations, but you can also use it to go from the standard form of a quadratic function to the vertex form. Now, we've also learned that any quadratic function of the form y equals a squared has a turning point at 0, 0. That's actually extremely important, right? Any quadratic function that has the form y equals a times x squared has a turning point at 0, 0, all right? Any quadratic function of the form y equals ax squared plus bx plus c can be written as a shift of y equals a times x squared. So, let's take a look. Any quadratic formula y equals ax squared plus bx plus c has an equivalent vertex form y equals a times x minus h squared plus k, where h, k are the coordinates of its turning point. And again, it's real simple, right? The idea is, I take y equals ax squared, I shift it h units to the right and k units up. Again, this is assuming h and k are positive numbers, and I've got now my vertex form. Let's take a look at exercise number 4. Consider the function y equals 5 times x minus 4 quantity squared plus 20. Letter A, at what coordinates will this function have its turning point? All right, this is simple enough, right? Pause the video now and see if you can figure out where the turning point of this function is. All right, well, it's kind of simple, right? What we know is that we know that this function is simply a shift of y equals 5x squared by 4 right and 20 up. But the thing is, 5x squared, y equals 5x squared, still has a turning point at 0, 0, right? We've seen that. Y equals ax squared always will have a turning point right at the origin. And therefore, the point 0, 0 ends up at the point 4, 20. The 5, right, all the 5 is going to do is stretch our function vertically or compress it, right? Well, in this case, the 5 is going to stretch it. It's not going to compress it because it's larger than 1. Now let's take a look at letter B just to make sure. Provide table evidence to support your answer from A. In other words, I want to see in a table without any question that our turning point is at the point 4, 20. Now let's bail out of here. All right, let's open this thing up. Let me open up just a brand new document. Okay, let's add a graph, right? And what was it? It was 5 times x minus 4 quantity squared plus 20. Whoops, plus 20. There it goes. Enter. I don't even see the graph on here. And that makes sense, right? If the turning point's at 4, 20, it's somewhere way up there, plus this parabola, given that it's got a leading coefficient that's positive, is opening upwards. So let's go into the menu and let's just take a look at our table. Okay, remember, my take on it is that this turning point is going to be at 4, 20. So let's like really hone in right around that 4. So here I've got 240, 325, 420, that's in theory my turning point, 525, and 640. Look at the symmetry there, 40, 40, 25, 25, and then the point right in the middle must be the turning point. In fact, let's write down that evidence on our sheet, okay? And let's write a little bit of that table down. X, Y, 2, 3, 4, 5, 6. At 2 we have 40. At 3 we have 25. At 4 we have 20. At 5 we have 25. And at 6 we have 40, right? Whoops. Look for the symmetry, and there's our turning point. Right? And it's great because that means we don't even have to have a leading coefficient of 1. We can always see the vertex or the turning point by just looking at these two numbers. And yes, it's a bit confusing because it will literally be the opposite of that number, right? There I've got sort of a -4, if you will, whereas the turning point's at +4, and there I've got a +20, and there it's 20, right? And that's happening because, again, that horizontal shift is a bit counterintuitive. -4 is forcing us to the right by 4 units, all right? But still, you know, that is the way it is. So let's take a look at one last little piece. The vertex form of a quadratic function or parabola can be very useful, extremely useful, when modeling real-world situations. And let's take a look at one of those in exercise number 5. The domed roof of a greenhouse has the shape of a parabola shown below. This shape can be modeled by the function y equals a times x minus h squared plus k. Letter A, what are the coordinates of the turning point of this parabola? All right, that should be a piece of cake. Pause the video now and just write down the coordinates of the turning point. All right, well, it's simple enough, right? Turning point's right up here. That's at 10, 12, so easy enough. 10, 12, no problem. Let's take a look at letter B. Fill in the values of h and k in the formula above based on your answer to A. All right, so in other words, like h comma k, right, literally, these are the values of h comma k. So now I can just write this down. Y equals a times x minus 10 quantity squared, don't forget the squaring, plus 12. If you don't have the squaring there, then this is no longer a quadratic function, but only a linear function, right? So there you go, y equals a times x minus 10 squared plus 12, right? We know the formula for this at that point. The problem is we still don't know the value of a, right? I'm trying to model this roof using an equation. I still don't know the value of a. So now let's figure it out in letter C. The point 0, 8 lies on this function. That's the point right here, okay? Use this point to determine the value of a. State a final formula for the function shown graphed. Verify using the calculator that it is correct. All right, so this is cool. Anytime we've got a function, all right, and we did this, by the way, back when we were coming up with the equations of lines, which seems like years ago, right? But whenever we have a function and we're just missing a parameter, right, that's that leading coefficient that we're missing, but we know a point that lies on this function, we can just substitute it in. So I'm going to put in 0 for x, and I'm going to put in 8 for y, okay? So 8 for y, and 0 for x, and now I'm going to solve for a. Now you might ask, why did I choose that point? No reason, really, except that it was convenient. In fact, the only point you couldn't substitute up here and figure out what a is the turning point. We've already kind of used that one up to figure out what h and k are. But you could have certainly used the point 20, 8, and if you like that better, that's fine. I think there's also another nice point right around here that you could use to figure out a. I just think that the y-intercept is convenient. It's sitting right there. Anyway, so now let's solve for a. Now this is going to take us a little bit of work, but not too much. Here we've got a times negative 10 squared plus 12, right? Negative 10 squared is 100. So we're going to have 100a plus 12. All right, to solve that for a, I'm going to subtract a 12 from both sides. It's a little bit of a funny 12 on the right-hand side, but we'll deal with it. 8 minus 12 is negative 4 equals 100. Equals 100 times a. A is going to be very small and often is in these problems. All right, so I divide both sides by 100. And because dividing by 100 is pretty easy, I'm not going to break out the calculator yet. A is going to be negative 0.04, right? 4 divided by 100 is equal to 0.04. Negative 4 divided by 100 will be negative 0.04. So now I know my a. Now I've got my entire formula. Right? My entire formula is going to be y equals negative 0.04 times x minus 10 squared plus 12. That's in theory the formula for this parabola. And by the way, let's talk about a couple things. One, I'm not surprised that it's negative. I'm not surprised it's negative because the parabola opens downward, and we know that the leading coefficient has to be negative if a parabola opens downward. In fact, if I had made some kind of mistake, and I'm not sure what, maybe I did 8 minus 12 equals positive 4, that would be an easy mistake to make, right? Then I would have gotten 0.04 instead of negative 0.04, and I would have known it was wrong because the parabola opens downward. The other thing is I'm pretty comfortable that it's a number less than 1 because it looks like the parabola has been kind of squished, right? It's been compressed. You know, our normal parabola is much more narrow. This is far more wide. But let's make sure it's correct by putting it in our calculator. Let me bail out here. Let's open this thing up. Again, one last time with a brand new document. Nope. Let's add a graph. All right, this is going to be negative 0.04, that's 0.01. Let's try that again, 0.04 times x minus 10 squared plus 12. All right, let's just make sure that's right. Negative 0.04 times x minus 10 squared plus 12. I hit enter. Now, of course, that doesn't even vaguely look like what my graph is over here because the window is completely different, right? This is the dome on a building or something. The horizontal axis goes from 0 to 20. The vertical axis goes from 0 to 15. So let me change all of that in my window settings. I'm going to go 0 to 20. Actually, I'm going to make that a little bit smaller than 0. I'm going to go up. I'm just going to go to negative 1 so I can see the axis. Then I'm going to go to 20. Same thing on the y min. I'm going to make that negative 1. And then on the y max, I'll go 15. If I don't give some negative values of y, I'll never see the axes. And there it is. All right. I could even put a grid on here, and then I'd be able to like really match it up. But I think I have some confidence that I've done this problem right at this point. Now, I mean, keep in mind, right, an easy mistake would be to botch the a, right? You could botch the a, you could make it positive, right? If I had made it positive, let's try that again. If I had made it positive, then look what would have happened. I got to get all the way over there, right? Just delete that out, right? I would have exactly the same parabola with exactly the same turning point, but it would be opening upwards instead of downwards, and I would know that that would be a roof that would fill full of water. Right? It wouldn't be a dome anymore, it would be a bowl. So we can verify that we've done things correctly by using our calculator in appropriate ways. All right, let's wrap this thing up. There are many different ways that we can write a parabola. The most common way is literally the standard form, right? The standard polynomial form, a times x squared plus b times x plus c. We also saw today that if you can write it in factored form, you can see the zeros quite well. But really, the thrust of today's lesson was the vertex form of a parabola. That's when it's written as a times x plus or minus a constant squared plus or minus another constant. When it's written in vertex form, we should be able to very quickly and easily see what the coordinates of the turning point are. And in very practical settings, when we already know what the coordinates of the turning point are, and one other point, like in that last exercise, the y-intercept, we can actually come up with the vertex form and the equation of that parabola. It's really kind of cool. And it's sort of the culmination of everything that we've done in this particular unit. That last problem, in fact, had a horizontal and a vertical shift. It had a vertical compression, that 0.04, and it even had a flip because it was a negative 0.04. So lots of different things got involved in that final problem, almost everything that we did in this particular unit. All right, you'll see function transformations a lot more in other courses. No more in this course because we only have one unit left to go, and quite frankly, that's on statistics. For now, I want to just thank you for joining me for another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.